These are the notes for Unit 6, Day 8, and they start on 25-year packet. And the title of this is Finding Antiderivatives in the Definite Integral Values Using Basic Rules. So our essential question is, how can I incorporate what I know about derivatives to find antiderivatives? So we've been working now with a rate of change and accumulating that rate of change, knowing that what the information we get from that process recovers information about the original function. We've landed on standardizing our terminology. That accumulation process we're calling the definite integral, or in some cases we'll call it the antiderivative. The definite integral, and then the function we end up getting information about is we're calling that the antiderivative. That's that original function. So if we go back to our function that we've looked at a lot in this unit, and that's 2x, that's that linear function that we accumulate underneath. We saw that when we collect data on that function, we end up with x squared. So we can see then the relationship between this function here, if differentiated, gets us this. So just to kind of discuss what's happening here then, if we notice, if these three functions are kind of like in the x squared family, they're all parabolas, they all just have different intercepts. But if we differentiate each one of those functions, we get the same derivative. So it kind of leads to the discussion of, if this is what we are accumulating underneath, then how do we know we end up with this or this or this or this? And the answer is we don't, unless we have more information. So these are all the derivatives, and they all come from these antiderivatives. And so the idea then is, it doesn't matter if there's a numeric constant out here or not, it will end up having the same derivative as anything in the x squared family. So then the antiderivative in generic terms is just that. It's that function we get, that original function that when differentiated gives us our rate of change here. And we could have any numeric offset here. This is basically the y-intercept. So we could shift that in the sense of specifically of this quadratic, we could shift that parabola vertically in up or down. It doesn't matter. We would still end up with the same derivative. So looking at this, then we're gonna tie this into how we can use our derivative rules. So for instance, if we start with 2x, I think it's pretty easy to speculate what you started with, that when you differentiate you get 2x, and that's x squared. But if you look at our power rules, really what we're doing to get the antiderivatives, we're reversing that. So if you think about the power rule, right, you've got the power, you bring down that old power, multiply it by the coefficient, and then you reduce the power by 1. That's if you differentiate. So if you reverse that process, then we're going to be increasing the power by 1. And instead of multiplying by the old, we're going to divide by the new. So it looks kind of like this. If this is a polynomial, it's x to the n power, then its antiderivative has an n plus 1 power, and then we divide by that new power, n plus 1, and then we put the plus c on the end. And so this represents the family of antiderivatives that come from this derivative. So just in terms of specific to the power rule, don't forget these strategies that we used when differentiating. They still apply for antiderivatives as well. If we have like something squared, something in brackets squared, we're going to FOIL that out. We're going to take roots and convert them to fractional powers so that we can reverse the power rule. We're going to take denominators, variables in the denominator, rewrite them as negative powers, so we can use the power rule. So all of those strategies we're going to continue to use. So let's try these 3 problems that will kind of highlight each strategy. So this is just a straight power rule. So the 5 is a coefficient. We're going to bring that out front just like we did for differentiation. And then we're going to have to bump up this power. So it starts as a 3. The new power is 4. We're going to divide by the new power 4. So the antiderivative is 5x to the 4th divided by 4 plus c. When you differentiate this, if we just do a quick check, if we differentiate this, we bring down the power of 4 and multiply it to make a 20. 20 divided by 4 is 5. And then reduce this x cubed. So we end up getting back that integrand when we check our work by differentiation. Let's take a look at this next one. So here's a cubed root. So I'm going to rewrite that root as a power. I'm going to bring the 5 out front because I'm really concerned about doing the power rule just on x to the 3rd power. So remember the strategy here when we have to change this power, whether it's adding or subtracting, we want to think about, in this case, we're going to add 1. We want to think about that as 3 over 3. So in my head, I'm thinking x to the 1/3 plus 3/3. That is increasing the power by 1. So we're going to get x to the 4/3, and then we're going to divide by the new power, 4/3. And this looks a little clunky, but if you get into the habit of just increasing the power by 1, dividing by that new power, and then give yourself a step to work out the math, then you're not doing too many things at one time. It's harder to make a mistake. And then the plus c on the end. Okay, so now we can kind of clean this up. We know dividing by 4/3 is the same as multiplying by 3/4. So if we multiply by 3/4, we're going to have 15 over 4, x to the 4/3 plus c. Let's take a look at this last example here. We've got an x cubed in the denominator, so we're going to rewrite that. Oh yeah, before we look at that, I want to just kind of highlight this. X to the 4/3 power is the same as saying the cube root of x to the 4th power. So just recognize this as an equivalent expression. It comes in handy for multiple choice questions. All right, getting back to this, we're going to rewrite this as 5x to the -3rd power dx. We're going to remove the 5. We're going to concentrate on doing the power rule here. Now remember that this is a negative power, and 1 bigger is moving to the right on the number line. So 1 bigger is -2. So this is going to be 5x to the -2 power divided by -2. So increase the power by 1, divide by the new power. And then we're going to put our plus c here. And I'm just going to clean that up. I'll call that -5/2 x to the -2. In fact, I can clean it up a little more by taking this x to the -2 and relocating it and giving it positive power. So that would be the antiderivative for this problem. So we're going to go through then a bunch of examples here. And the really handy thing would be to have a derivative flipbook out to try to reverse some of these more common rules that are not power rules. So it's not a power rule reversal. It's a matter of knowing what you started with. And in that case, knowing the derivative rules really well. So if we look at this number example 2 here, 1 over x dx, this is a rule 23. We know that if 1 over x is the derivative, then we started with natural log of x, of the absolute value of x plus c. So the natural log of the absolute value of x is the antiderivative of 1 over x. Sine of t dt. So if you know you differentiated and you got a sine, you must have started with a cosine. But if you start with a cosine, then you have a negative sign for a derivative. So this must be, this is a rule 10, this must be negative cosine plus t plus c. Number 4 is rule 21. So e to the u, we know that we have to start with e to the u in order to have the derivative be e to the u. Remember that exponential is the derivative of itself, so it must be the antiderivative of itself, and then plus c on the end. So number 5 should be a familiar pattern. It's a rule 2. So we've got h, trying to find the antiderivative of h of x times j prime of x plus h prime of x times j of x. And so that unique pattern is a product rule. So the antiderivative then must be h of x times j of x plus c. So differentiating this, you need the product rule in order to express the derivative. Okay, so making things just a little more complicated. this is a rule 9, but this is with a chain rule. So we know that we need to start with a sine to get a cosine. So the antiderivative must be sine of 5x. But if we differentiate sine of 5x, we get cosine of 5x times 5. So if you notice, here is the derivative of the inside. So this is a derivative with a chain rule already expressed. So this is the antiderivative of sine of 5x plus c. So let's see if you can see the chain rule in this one. So stop the video and try to think about what the antiderivative is here. So looking at this, then we see that we have an e to the 4x cubed, and the derivative of 4x cubed is 12x squared. So the antiderivative, this is a rule 21, the antiderivative must be e to the 4x cubed plus c. And then 8 is a pattern you need to be able to recognize, and it's a rule 15. So go ahead and stop the video and try to do this one. So recognizing this pattern then of having the radical 1 minus x squared, this is an inverse sine of x plus c. So this is the antiderivative of this. And then, oops, I forgot the times 2. Let me just add the times 2 in there. There we go. So that's from having the 2 up top there. Okay, and then this last example is to find a function h of x such that h prime of x is this. So this is the derivative. So this is kind of a combination of rule 11 and 12 in your flip book. And so h of x then is going to be, if this is the derivative, we must have started with tangent. So for tangent x, when we differentiate that, we'll give us 4 secant squared x. And then we have a minus sign here. This is a little bit tricky. We know that we must have started with a secant, and in this case, a secant 3x, but that has a chain rule in it. So this antiderivative must be 2 secant 3x. And then that way, when we differentiate this with the chain rule, we end up with a 6 on the outside as a coefficient, and then our plus c on the end for the antiderivative constant of integration. So when we get back to class, then we'll go over the takeaways and work on recognizing more antiderivatives.